Recording in.
Do you have a pointer? No, maybe I just use the computer. The analogical one. Ah. Well, otherwise I just use the gesture pointer. No. This one.
Device with pointer, but now it doesn't.
Ah, okay. Do this. Well, I just need a pointer in the end. This is fine. Yes. Move this. Ah, no.
If not, you can use this.
Ah, yes. Thanks. Okay. Okay, thank you. Okay. Ah, but just no, because he asked me to. No, it's fine.
Yeah.
Identify your keyboard. Keyboard. Identify. Okay. Let me see. Ah, it works. Yes. So no, this doesn't. Okay.
So let's start. I guess we have already 10 minutes over the show. So today we have Fabio today from Italy, from Pisa, Nest Nanosi NR and Scuola Normale Superiore. I guess is this Scuola Normale for entire Italy or for Pisa?
Oh, only Pisa.
For Pisa, okay. So, and he will talk us today about thermoelectrics and thermal transport in hybrid terminal systems.
Okay, thank you very much, Misha, for introduction and for the invitation. I'm very pleased to be here. So today I will speak about mainly about a project which is about the separation of heat and charge, in implementation of separation of heat and charge fluxes in a hybrid superconducting quantum Hall system. And then, if I will have time, I'll also mention another project which is not strictly related, but it's also something which we are working on. So I should also mention this project. It's from the Italian Ministry of Research, which is funding my research nowadays. So the outline of the talk is the following. So I will give an introduction, a brief introduction on thermoelectricity and heat engines. Maybe it's completely useless in this audience, but I don't know, maybe for some people it can be useful. Then I will start, but taking the problem from a bit far. So I will first introduce the three-terminal heat engine, just to see what happens when you have when you add a terminal to the usual two-terminal system. Then I will speak about how we can get heat charge separation in a three-terminal system. And finally, I will discuss how to implement it in a quantum Hall superconductor hybrid system. Then, as I said, if I have time, I will say something about a work we've done on thermodynamic uncertainty relations in the absence of time reversal symmetry. But this, I think, I will just mention in the end. So thermoelectricity. So our main object is a conductor where. So I'm just saying the very basic notions just to be sure that we are all on the same page. So we have a conductor to which we apply two terminals. The two terminals can have different voltages. So we have a different a voltage difference delta V, and can have a different temperature delta T. Because of this, we will have a charge current and a heat current flowing through the conductor. So we are neglecting phonons. So I'm only speaking about electrons. We are thinking of very low temperatures. So somehow we either they are not important or we are getting rid of them. I mean, we are not considering them. So just let me introduce the transport coefficient in the linear response. And we will see in the next slide why I introduce them. So first, the conductance, we are all familiar with that. Which is the charge current divided by the voltage at equal temperature. Then the second quantity coefficient is the thermal power, which is the voltage, which is the related to the voltage which appears at the ends of this conductor when a temperature difference is applied to the conductor. This is calculated at open circuit. So you apply a voltage, you apply a temperature difference, some voltage will appear in order to stop the current from flowing because it's open circuit. And the third one, it's the thermal conductance. So similarly to the conductor, is the heat current divided by the temperature difference, again at open circuit condition. So why I'm speaking about this? Because these are the transport coefficients which are important when you think about your system as a heat engine. So as a system which converts heat into usable work. So schematically, a heat engine is something which absorbs the heat. So schematically, something which is connected to two thermal baths. One is hot, the other one is cold. So a heat current which will exit from the hot reservoir. A charge current will be also present. When this charge current goes against the voltage which is applied, we will get some power out of the system. This is the heat engine, so which converts a heat current into electrical, in this case, electrical usable work. So we can see in our schematic, in our preferred system. So this can be viewed as a heat engine when we applied to the conductor a temperature difference. The efficiency of this heat engine is defined as the ratio between the power which is generated divided by the heat which is entering the system. So the heat which we are providing the system. So in order to make sense, the power must be positive, of course. So what is interesting is that in the linear response, all the performance of these heat engines are determined by a single figure of merit, this ZT figure of merit, which is written just in terms of the transport coefficients I just was defining. So the conductance, the thermal power to the square, and the thermal conductance. So when you are dealing with heat engines, these are, at least in the linear response, these are the quantities which you need just to assess the performance of the heat engine. So as I said, these characterized completely in the linear response in the sense that you can write the maximum efficiency of your system in terms using this expression here, which contains the Carnot efficiency, which is the maximum allowed by thermodynamics. So in this case, I think I wrote it here. So it's just one minus cold temperature divided by hot temperature. And this expression here, which is just in terms of ZT plus 1 square root and all the rest. And you can also characterize the maximum output power, which is written in terms of conductor GA squared, conductance thermal power squared. and also the efficiency at maximum power. Now, why people are why interesting to look at thermoelectricity at the nanoscale? So why people are looking at the nanoscale? Because usually this ZT figure of merit, it's very small in materials. And people starting already in the 90s, people started to think about how can enhance this figure of merit using a nanoscale system. And already in these two papers here, they find that when you have some kind of energy filtering in your transport coefficient, you can enhance a lot your performance of the system. So in this case, they studied a multi-layer, finding that when you decrease the spacing between the layers, the ZT went up. In this case, they did a study of how to maximize the ZT, finding that you can maximize it when your transport coefficients are like delta function, are very energetically sharp. So nowadays there's a vast review on. There are lots of paper on this. Now the thing is that in two terminals. So as I said, you want a big ZT, and to have a large response, you have a big also thermal power. This is what you want. And in principle, you want to control separately conductance, charge conductance, thermal conductance, and thermal power. But this is usually not possible because, for example, due to Wiedemann-Franz law, thermal conductance and electrical conductance are strictly related. Actually, their ratio is equal to a constant divided by temperature, is equal to a constant which just depends on fundamental constants. So this makes a big constraints, and that's probably the main reason why ZT is not. Is one of the reasons why it's difficult to make a large ZT. So one way out to get to enhance the performance of heat engines is to use multi-terminal systems. And what we want to do now is to use multi-terminal system actually to have a separate control of conductances, of thermal power. And in the end, what we speak about is how completely decouple the heat flow and the charge flow. So in the end, I'm going to go into this direction to see how to decouple these two flows. So let me first say a few words. I won't spend much time on that, but I just want to say a few things. So just consider a three-terminal system, completely general. So if a conductor attached to three terminals with different temperature, different chemical potential in all the leads, you just order the temperature, for example, in this way. So in this paper here, we developed the theory in linear response to characterize the system from a point of view of a heat engine. And we basically define some non-local transport coefficients. So in this case, because you can apply voltage between 2 and 1 and look for the current flowing into the third. So you have got all kind of non-local effects going on. And then we find that you can generalize, you can find generalized figure of merit. So there is not just one ZT, you need at least 3 different figure of merit if you have this three-terminal system. And then you find that efficiency and output power can be increased if you have this more freedom. So you have a freedom of having one more terminal. And so just to mention a strange thing you find is that can have different. So the Carnot efficiency is not simple. Does not simply depend on temperatures. If the 3 temperatures here are different, but the Carnot efficiency depends on which heat currents are on which of these heat currents in 1, 2, and 3 is positive. So it's going into the system because the efficiency because only the heat current which enter the system contribute to the overall heat current which can produce work. And you find strange quantities, strange expressions like this. So the Carnot efficiency, in the case that only from 1 you get a positive heat current, is something which contains the usual Carnot efficiency between the two extremal temperature, and then you got an additional term, which actually depends on the value of the heat current you have. Okay, so this just to set the stage. Then what I'm doing now is to introducing a new ingredient, so superconductivity. And the idea is, in order to separate charge and heat, we can use a superconductor. But I will explain a bit better in a moment. Since a superconductor doesn't allow a heat to flow. It's like a mirror with respect to energy. I will explain why in a second. So we want to have a three-terminal system plus a superconductor. So the first idea which came to our mind was to have a three-terminal system where you have a normal contact, a superconducting contact, and then a voltage probe. So these already by construction allow the separation of heat and charge. Why? Because through the superconductors, at least if voltages and temperature are smaller than the energy gap, I will come to this, in the superconductor, no heat current can flow, but only charge current can flow. In the voltage probe, no charge current can flow by construction, because in the voltage probe is defined as a lead where the charge current is equal to 0. Because the voltage, the chemical potential of the probe will adjust in order for current not to flow. And so here you have simply heat current. So you separate charge flow from heat flow. This is not really a system. This is a setup in which you can realize heat charge separation. So in this paper here, so almost 10 years ago, what we wanted to do was to check how the performance of a heat engine can improve by separating heat and charge. So the idea here was not to propose a system which does heat and charge separation, but to see how charge separation can be used to increase, if really increase the performance of a heat engine. So now let me go back a second to the superconductor. So why heat current in the superconductor is not, why there is no heat current in the superconductor? So the starting point is the spectrum of excitation in a superconductor. So energy versus wave vector momentum. So the spectrum is something like that, which presents a gap. So there are no excitation for energy below this delta, which is the order parameter of BCS superconductivity. And there is a gap. So since the energy is carried by quasi-particles, so everything happening at the energy below delta doesn't contribute to the transport of energy. And this is the basic idea of using a superconductor to stop heat flow. And moreover, so heat cannot be carried by the condensate. So there is no heat current, at least for energies below delta. Then above delta, yes, you've got quasi-particles, they can carry energy. But if voltages, so if your energy scales in the system has more than delta, there will be no heat current. Nevertheless, there can be charge current in the superconductor, because for every charge current, what you need to do is to transfer a pair of electrons from. So let's look at this picture here. We have a normal metal in contact to a superconductor, and what you need to do to transfer charge is to transfer a pair of electrons from the normal side into the superconductor. They just join the condensate, and they just condensate, and the current can flow. From a microscopic point of view, we speak about Andreev reflection as the basic mechanism of this. So Andreev reflection is a process for which an electron which impinges on the interface, then returns back, instead of returning back as an electron, as a specular, it can come back as a hole having the opposite charge of the electron. This is basically, it is like saying a pair of electrons entering the superconductor. So in a superconductor, below the gap, no heat current energy can flow, but charge current can flow. So we can say the separation, at least in the superconductors, occurs in this way, because heat. So let's say energy and charge are really decoupled, are carried by different, are really decoupled, let's say this. So to check whether this three-terminal plus superconductor system can do something useful, we just consider this setup. We have the normal terminal with chemical potential μn, temperature Tn, the superconductors with chemical potential μs, temperature T. This is the base, would be the base temperature. The probe with mu chemical potential for the probe and the temperature. This, in the end, can be described by two terminal systems, because first of all, this mu. Because of conservation of charge and energy, and because this mu p must be determined self-consistently in order to have a zero current here. So, but what I want to say is that what we do, we model the conductor with a scattering matrix. I mean, parameterizing the scattering matrix with the minimum amount of parameters. And we did a small temperature sum effect expansion. So we have some set of parameters which we can play with. So we don't know exactly what they are physically. We know that they enter the scattering matrix. So we don't know exactly which system physically we are considering, but we know that we are changing some parameters. And we want to see what happens by changing this parameter, how we can play with the heat, with the transport coefficients, at least in the linear response. So, for example, these are some results which prove the fact that you can violate Wiedemann-Franz law.
What does the parameter?
So these are the parameters which enters the scattering matrix of this system here. You have a system, you don't know what it is exactly, but you know that it can be described by a scattering matrix.
The 6 comes from unitarity also.
Exactly. Unitarity plus you're imposing small temperature, which also includes, gives some more constraints. So you constraints by unitarity, small temperature, and I think that's it. You don't, yes, I think these are the main. General, yes. Yes. It's not completely general. I think it's the minimum amount of parameters, but it's general in this sense. You've got many. There are already too many, so they are already a lot. So, sorry. Yes, because we want to be in the linear response. So they have to be small, but also have to be small because we have a superconductor, so temperature must be smaller than the critical temperature, so which is already a small temperature. So everything is small. Oh, I mean, all temperature are small in the end. So then here, what I plot is the ratio between let's say the Wiedemann-Franz ratio between thermal conductance and electrical conductance. which is divided by lambda 0, which is the Lorentz number I was speaking about before. So it should be, so this ratio, lambda divided by lambda 0 should be 1. And here we say that but by fixing all the parameters but 1, this rho 2, 0, it's one of the parameters, you can, this lambda, this ratio can be controlled can be controlled going from 1.1 to this to 0.4. In this case, we just fix the parameter in such a way that k is fixed. So we are varying just g. This is one possible way to do it. So this is not very important. It does what I'm showing is that you can really control this this ratio here, and at the same time you can control the the thermal power. Thermal power, which is non-monotonic, but this does all depends very much on the parameter. This is just to show that you can control the 3 G, K, and S in an independent way. Okay, so maybe this also shows that you can. It seems like you are just using a different parameter, but this is not very important. But more importantly, here we compare the performance of a heat engine, the performance of a two-terminal system with this three-terminal system with superconductivity, with superconductor. And what we do, so it's a statistical analysis, and this is a plot which is basically the correlation between Q. Identifying Q. Q is the power, is this GS squared basically, is the power factor. Is the power factor. I didn't define that. So it's the one which controls the output power. So so each point it's a given realization. So it's a given choice of parameters. So since we don't know exactly which system we are considering, we just take at random some parameters, some set of parameters. We put a point here, which gives you the value of Z and the value of Q. So what you want to be in this region here, IQ, so high output power, high ZT. You want to be here. So from this statistical analysis, what you find is that for the two-terminal system, you get up to here. So basically, it's contained, all the possible systems are contained in this kind of rectangle here. If you have these three terminals plus superconductor, you are in all this region here, which means that you can double the ZT and you can double the power output. This gives you an idea that how we can for a completely generic system. So this tells you that reaching this independence between the transport coefficient gives you some freedom to get a better performance of a heat engine.
Sorry, but extreme points seems to be quite sparse. So it means that there exists only small space in the surface.
Yeah, probably. I think so. Yes, there is this small space. Yes, this is yes.
But do you think still is realistic to?
So if you know exactly which is how to realize this system here, you basically are done. And the thing is that we know which are the parameters so we know that this point here corresponds to this scattering matrix here. But then how to do it? So the best performance is found for this point. So maybe there's another point above this. I don't remember how many systems we looked at. So the point was not to